Welcome back everyone to EGME-333 Fluid Mechanics. In this video we're going to be discussing control volumes. So to define a control volume, let's think of it as an arbitrary volume in space that is enclosed by a control surface and is independent of the fluid mass that flows through it. For example, let's consider the flow through this pipe section. If I isolate the region of space defined by the inner walls of the pipe system, I can consider that to be my control volume, where the control surface is composed of the inner walls of the pipe and this region, point 1, where flow is entering the control volume, this region here, point 2, where the flow is exiting the control volume, and this region here that is also exiting the control volume. Notice that the control surface may be real or imaginary or a combination of both, as in this case. It's important to note that a control volume can be fixed in space as it is in this example. However, a control volume could also be moving in space. For example, if I define a control volume that is fixed to a jet engine, this control volume may be fixed in space or moving depending on whether the jet engine itself is either fixed in space or moving as well. One thing I'd like to highlight or re-emphasize is that in a control volume, we are not so concerned with the mass contained within it, such as when we look at a fluid element at time equal t sub 1, as this fluid element enters the control volume, at some time later t sub 2, the fluid element will have entered the control volume, traveled through the jet engine, be exhausted by the jet engine, and eventually have exited the control volume at some later time, which we label here as t sub 2. Additionally, the shape of the control volume does not have to be fixed. Control volumes can have a deforming feature, such as in a deflated balloon where the control surface is defined by the inner walls of the balloon. So with increase in time, in this example, the size of the control volume will decrease. One thing to highlight that if this balloon isn't fixed in space, or there's a force holding it in place, then this control volume will not only be deforming with time, but will also be moving in time if we allow the balloon to travel. There are two ways to describe control volumes. They are either through a Lagrangian description or an Eulerian description. In the Lagrangian description of a control volume, the control volume moves with the fluid. So no fluid is allowed to pass through the control surface, such as in a control mass approach, where the control surface or the velocity of the control surface is locally defined by the corresponding local velocity field. In the Eulerian description of a control volume, often the control volume is fixed in space, or itself can also be moving. However, the key difference is that the fluid is allowed to freely pass through the control surface, where you might have mass flow entering the control volume, and simultaneously there could be mass flow exiting the control volume.